Hi, in this video, I'll demonstrate how to do regression. I'll split this tutorial into 3 sections. The first section, we will do a scatterplot analysis. In the second section, we'll do a correlation analysis. And in the third and the last part, we're going to do the bivariate regression. Suppose that we have a data set, and we are going to use the data set called Digital Literacy for Elderly. So this is a survey on what happens to the elderly who has received digital literacy training. So in the data set, we are very interested in understanding the relationship between digital training as the independent variable and digital skills as the dependent variable. So we have a hypothesis which says that digital training is positively associated with digital skills. Now, the first thing what we want to do before we do a regression analysis is just to check the scatter plot to see whether the data points on digital training has any trends or have any relationship with digital skills. Now, please open up your tutorial file, the Word file, to follow this step by step. I'll demonstrate this in the video. So first of all, make sure that you have access to the Excel raw data file for digital literacy for elderly. And secondly, I want you to upload your file to SPSS. So this is the raw file in Excel that I have uploaded to SPSS software. So the first thing that we will do is we'll do a scatterplot analysis. We'll go for graph, legacy dialogues, and the scatterplot. So I'll go for graph, legacy dialogues, scatterplot. I'm going to choose just a simple scatterplot, define it. Let me reset. My interest is to look at the relationship between digital training as my predictor variable. So it's a predictor because I'm using digital training to predict an outcome. So digital training is my independent variable. And independent variable is always on the x-axis or the horizontal axis. And the outcome that I'm trying to predict is called digital skills. So digital skills is my dependent variable. So dependent variable is always on the vertical line or the y-axis. So I'm going to give a title to this scatter plot. You can follow this and replicate the steps. And I can click OK directly or paste. I like to use paste because I can see what exactly I'm going to do. I can remove this part. This was the previous analysis. I have a graph here. This is the instruction that I've just given to the data. Give me a scatter plot of this variable as my independent variable, and this is my dependent variable. And this is a title that I add. I'm just going to arrange them and click run. There you go. It shows me a scatter plot. Don't look at this because this is from the previous analysis that I did. The scatter plot shows a pattern of the relationship between digital training and digital skills. Do you see a pattern there? Of course, there's a pattern. Have a look at this guy. One respondent who only joined 2 times of digital training have a score of 40. And there are quite a number of people here. Let's say this person who have joined 3 times of training and has a digital skill score or receive a digital skill score. This is a form of test that we give them, right? And this person will receive around, let's say, 64 or 65. And there are some people who join 4 times, and they range from this low to this high. Let's say this person received around 73 score for digital skills. And there are people who have joined 5 times. So you can see actually there's a kind of a pattern that goes through like that. That shows a linear relationship between digital training and digital skills. But this is just an observation of the data, right? So we need to look at the correlation. So that brings us to the second step, which is to look at the correlation between the two variables. Okay, now let's go back to our data set in SPSS. Go to Analyze. So this is, we're going to do bivariate regression, the bivariate correlation, the correlation between the two variables that we are interested in. So go to Analyze, Correlate, Bivariate. So we're interested in the relationship or the correlation between digital training and digital skills. We're going to click means and standard deviation. I'm not interested in changing the other function like style and bootstrap. We don't need this. But the key part here, we want to show a Pearson correlations coefficient, which is perhaps the most widely used correlation coefficients in the world. And we are choosing the default setting with two-tailed test of significance. Two-tailed is less stringent. One-tailed is much stringent when you have a particular directions of way you think the relationship of the variables are. So I will choose two-tailed, which is the standard default test of significance. And most of all is this correlations that are statistically significant. You want to flag them. You want to tell us, show us the correlation coefficient, the Pearson correlation coefficient that are significant in stars. So this will be shown using stars. I can click OK or paste. I prefer to use paste. So there you go. My syntax that shows the variables that I'm trying to do the correlation analysis. And it also produces some descriptive statistics. So just going to run it. So basically, I have a descriptive statistics that shows the mean and standard deviation. So digital training, on average, of the 25 people who fill in the questionnaire on the digital training variable, have a mean value or average value of 4.04. And of the 25 people who fill in the questionnaire for the question on or the variable on digital skills, the average or mean score for the participants of 25 participants is around 62.2. So this is the key part that we are very interested in, which is the correlation coefficient table. As you can see, the diagonal up, we can ignore them. What we are interested in is actually the one that is below the diagonal. So is there a correlation between digital training and digital skills? This is where you look at it. So this shows that digital training and digital skills has a 0.714 correlations. Is that big? Is that small? Anything higher than 0.6 is already considered a high correlation. 0.8 is even super high. So 0.17 correlation. Remember, correlations ranges from 0 to 1. 0 has no correlation. 1 is perfect correlation, which means that perfect correlations means 1 unit increase of the dependent, 1 unit increase of the independent variable will be followed by 1 unit increase in the dependent variable. So what you have here is 0.17, which means that 1 unit increase in digital training is associated with 0.714 increase in digital skills. So this shows how strong is the relationship. Is it strong? Yes, it is strong. The second part is to look at, is this correlation statistically significant or not? And the answer is yes, because there are 2 stars that you have flagged, that SPSS have flagged for you. So it's significant at the 0.001 level. Remember this p-value at 0.01 level as a statistical significance test? It more or less tells you that the probability that this correlation coefficient is due to chance is very small. It's only at the it is only at the level of 0.0, only about 1%. So you are more likely to be 99% or 99 plus % confident that the result of this correlation is not by chance, but because it's really true. So okay, we have seen the evidence of a correlation between the independent variable digital training, and the dependent variable digital skills. Now, let's go to the third step, which is to look at the bivariate regression between the two variables. Okay, so let me just close all the files, which I think we don't want them to mess up. So in order to do the bivariate regression, just follow the steps that are provided. You go to Analyze, Regression, Linear regression. We're going to reset. Remember, digital training is our independent variable or predictor. Digital skills is our outcome variable or the dependent variable. Let's have a look. I'm interested in not changing anything. It's just there's a model fit and estimates. There must be a model fit. If there's no model fit, you cannot tell whether your regression, your regression line or the ordinary least square regression fit with the data or can explain the data, the observations that you have collected through the survey, right? And of course, I want to have the regression coefficient estimates. I can include descriptives if I want. I can include R-square change because I have only one independent variable. I'm not so interested about R-square change. I'm not worried about the plots. I'm not worried about the others. I'm going to use this default stopping. So I don't need to do even here the default stepping method criteria. Just leave it by default. Style bootstrap, leave it by default. And I don't even bother about the methods of entry. So this enter is a default function for regression, which means that if you have a bunch of independent variables that you throw in there to predict your dependent variable, they will be evaluated all at the same time, all at one go by SPSS. So I'll go for paste. I can check. What I like this doing the syntax is I can check what exactly am I studying before I really run the results. So I'm going to get mean, standard deviation, correlation, and the others. And I'm going to get the coefficient and also the ANOVA table and the others, pin up, pin, and pout. So this is part of the criteria that has been selected by the regression. As even so we have the dependent variable, which is the digital skills, and our independent variable is the digital training. So just going to run that. So here we go, the results from our bivariate, very simple bivariate regression. It shows that the same descriptive statistic as the one that we have seen early on. And the key part is the the correlation between digital training and digital skills is the same, 0.714. And is it significant? Is the ratio significant? Yes, it's significant at 0.000. And there are 25 people who fill in the survey for the variables, and we have entered. So this is the rest of these things. These are the important output for regression, right? So we have entered digital training. Look at B there, B. So which is model 1. So we have entered digital training. Sorry, A is here, A here, and which is here. So we have entered digital training as our independent variable into the model, and we have only one model because we don't have many variables that we want to assess in different models. And what this is showing, look at the R-square. What this is showing here is this R-square. This is very important. So this model summary table tells us that digital training explains 51% or 0.51 of the variation of the digital skills. Remember, our dependent variable is digital skills. Or you can also reverse it. you can say the variation of the digital skills, 51% of the variation of the digital skills can be explained by digital training. Is that big or small? I think that is pretty big, because you only have one variable, one independent variable. You can already explain more than half of the variation of your dependent variable, right? So the next part that I'm interested in is to look at the ANOVA table. Now, the ANOVA table is actually a table that tells us how well is the regression fit with the data, or how well is our data predict the dependent variables that we are interested in, right? So the model summary and ANOVA is tightly related, right? Later, in 2 weeks from now, we also have a topic on t-test and ANOVA. We'll look at that separately and in more detail. But why this ANOVA is shown in the regression analysis is because if you want to know whether your regression fit with the data, or you can say your regression equation that you're producing can capture or explain the data, the variation of the data that you have, and predicting the dependent variable that you are interested in, then you are more certain that the relationship between the two variables and the model that you are assessing is working well and is significant. So is the model here significant? Just to know that, you need to look at the F-test score. So the F-test gives you a 23.8. So there is a separate lecture on F-test and how to calculate it by hand, but normally we don't calculate it by hand because the statistical packages will produce that for us. The important part is the F score. The F-test is significant at less than 0.001. So what that means is that our model is significant. So that is a good sign. The last part, which is super important in any regression, is we want to know how big is the slope of this independent variable in predicting the dependent variable. So in other words, how important is digital training in predicting digital skills? So you can look at unstandardized or standardized beta coefficients here. Because I have only one independent variable, I can choose whichever I like, and I choose this one. That's pretty much fine. So what this is saying is that 1 unit increase in digital training is associated with 5.441 increase in digital skills, right? So that shows it is a positive relationship. But how big is it? It's a little bit difficult to know because we don't have other independent variables that are entered into the model. But the second important part you want to know after knowing how big is the beta coefficient is to know, is it a significant beta coefficient or not? And the answer is yes, because this 5.44 comes at less than 0.001. So it's significant. What it means is, or this p-value is saying that the beta coefficient or the slope in the regression coefficient that explains that the digital training has a 5.441 influence on digital skills, and this number 5.441 has a very low chance of have a very low probability that it happens by chance. And if it happens by chance, it's lower than 0.001. So 99-point-something%, we are certain. So 99.1%, which is 1 minus 0.001, which is 99.something%, we're certain that this number 5.44 is not due to chance, but it's due to the reality or the real thing, right? We can think of it that way. So I'm going to clear that. So the next part is to write up the conclusion, right? So we have finished doing the analysis, and if you just scroll through, you will look at how you write the conclusion of the analysis. So this is the equation. Remember, in any form of regression, you are interested in writing y equals to b null, or the intercept or the constant, plus or minus b1 x1. b1 is the slope, the beta slope. x1 is the independent variable 1. You may also have b2 that has its own slope called the slope is called b2. The variable is called x2. If you have a variable called x3, let's say x3 is another variable. For x3, it has a b3. So for every independent variable, it has its own beta value, or the coefficient, the beta coefficient that tells you how important. So what does this mean is that the digital training has a 5.44 influence to digital skills, but when this is 0, if this doesn't exist, digital skills start at 40.422. So it means that without providing people with any digital training, people will still score around 40 in the digital skills test, right? And what it means that if you give people 1 extra unit of digital training, then digital skills will increase by 5.44, which is 5.4 plus 40. If you increase this digital training by 10 times, this is what you're interested in, making a prediction. If you have 10 times of digital training, so 10 multiplied by 5.44, you've got 54.4 plus 40.52, you got like 90 something for digital score. So this is why regression is very useful, because it gives you the prediction, the ability to predict outcome using predictor. And what the data that you have collected either through survey or experiment, basically you are only collecting this variable and that variable. So you're collecting independent variable that you can ask people through survey, or you can provide people actual training, and then you measure your respondents or your participants' output score, the dependent variable, which is their digital skills, and you can give them an exam to take their score. Or you can ask them, if this is not a test, you can ask them about opinion or attitude or behavior, some sort of outcome that you can measure. So this is why regression is very useful. And then at the end, you will write the findings. For example, you can say, we have conducted a bivariate regression to test whether digital training predicts digital skills. And using the enter method, we found that digital training explains a modest amount of the variance in the digital skills score, with F123 at 23.89. So what is the F1,23? That relates to the ANOVA output. So we have an F, the F is 23.89, and there's a degrees of freedom that comes with F. So the degrees of freedom is 1 and 23. 1 for the regression and 23 for residual, because actually from the 25 respondents that we have, there's a certain way that the degrees of freedom is calculated. So it's often sample size minus 1. So we have 25 minus 1 becomes 24, and that is allocated along these two. So we have F1,23 equals to 23.89. Is it significant? Yes, at the p-value here, at the p-value that is significant, at a p-value of 0.001, and our R square is 0.051. Where is R square? Here, 0.51, right? And the analysis shows that digital training significantly predicts digital skills at this beta value of 0.544. You can be very consistent in terms of whether you're going to use 2 numbers behind the decimal or 3. And at t in bracket 24, t is actually the t statistics, and 24 is for this one, from the sample size minus 1. And then at the p-value of less than 0.05. So that digital skills at 5.44 is significant and has t-value of 4.88. This one. So therefore, the regression results support the hypothesis. And what is the hypothesis? If you forget, our hypothesis is this one, that digital training is positively associated with digital skills. So we support the assertion or the statement that digital training is positively associated with digital skills. Hopefully that's useful. You can review and rewind the video and to replicate the steps again if you miss any parts. Thank you. Bye.